Laws in dynamics. So recall Newton's three laws of motion states that an object in motion will maintain a constant velocity, either zero or some other velocity, unless acted upon by a net external force. All right, again, the idea being has to be a net external force, okay? So you can have forces acting on object, but if those forces are in equilibrium, which we'll review in a second, our object will maintain a constant velocity. Our second law is that the acceleration of a body is directly proportional to the net force acting on the body and inversely proportional to the inertia mass of the body, which makes sense. Again, you have a stronger net force acting on an object, the acceleration will be greater, whereas if you increase the inertia of the object, it will resist changes in motion, so the acceleration will be less. And then lastly, two objects, regardless of mass or charge, will always exert equal but opposite forces on each other when they interact. Do not forget this and do not mix this up with acceleration. The acceleration is what differs between the two based on the individual masses. So the forces will always be equal but opposite, but the accelerations can vary based on the inertia of the individual objects. Okay, so here's force versus mass. We have a directly proportional relationship. And then here's acceleration versus mass. We have an inversely proportional relationship. Vectors and components of forces. Okay, all force vectors must be broken into x and y components. So again, if we have like tension right here acting at angle theta, we're going to have tx and we're going to have ty, tx being the horizontal component and y being vertical component. Ty will equal t sine theta from the basic relation sine of theta equals opposite ty over hypotenuse t. And then t cosine theta will be equal to tx from the trigonometric relation cosine theta equals tx over t, adjacent over hypotenuse. Again, recall when you use Newton's second law, you must separate the x and y forces. They do not depend on each other, just the same way that horizontal and vertical motion do not depend on each other. So here are equilibrium conditions. Here's our characteristic. If we have motion, here's our characteristics of motion. If we have no motion, okay, we're moving at v equals 0, okay? We can say the object's at rest. And in the case of static equilibrium, our object's at rest and v is 0. We have 0 acceleration, which means our net force is equal to 0. In dynamic equilibrium, it's called dynamic because we're moving now. We have a constant velocity, so watch out for those key words, okay? Our acceleration is again none, and our balanced example in our net force is balance. Again, example, this would be a hockey puck sliding on ice. You have the force of gravity and the normal force of the ground counteracting each other. So the net force is 0, but your hockey puck is still moving at a constant velocity. And lastly, if we have a system that's non-equilibrium, the problem will indicate the keyword accelerating, or it'll ask you for the acceleration. In this case, the acceleration is not equal to 0, or the net force is not equal to 0. Okay? Solving dynamics problems. Again, the key steps are to draw a free body diagram of the scenario to visualize what forces are acting. Then you're going to sum together forces in the x and y directions separately. Cannot emphasize that enough. Okay? We're going to identify if the body of interest is in equilibrium or not in both x and y directions separately. So make sure you watch out for those keywords, or if it doesn't give you keywords, make sure you check to make sure the net force is equal to 0. Okay, we're going to solve for your unknown quantity. At times, this may involve switching from x to y or vice versa. Like we saw in the case of friction, in the case of, for examples where friction is acting, if we're working with kinetic friction or the maximum amount of static friction, we have to go to the y direction to solve for our normal force. Okay? Friction, static and kinetic. Okay? Static friction, the object is at rest, the force acts to impede motion, is the opposite, it acts opposite of the intended direction of motion. If your object is not at the maximum amount, then you cannot apply this formula right here. Your static friction is just an unknown. But if it's at the maximum amount, you can use, and you're given the coefficient of static friction, you can use this equation for the coefficient, for the force of friction equation, okay? Kinetic friction, if the object is moving, the force acts to impede motion again, and it acts opposite of motion. In this case, there is just one general equation to apply. All right, force of kinetic friction equals coefficient of static friction times the normal force. The coefficients for both static and kinetic are properties of surfaces, are properties of the surfaces in contact. They do not change between two materials. So if you took a table with a book on top of it to outer space, The table in the book aren't changing at all, so the static and kinetic frictions would be the same regardless of the fact that you've changed locations, okay? Another thing to point out is remember that the force of friction in both cases is not the same as the coefficients of friction, but they depend on the coefficients of friction, okay? So here's your general problem-solving strategy for objects, okay, that involve friction. You're going to check if the applied force is larger than the maximum static friction force, excuse me. If not, the object will remain at rest because the maximum static friction force is greater than the applied force, so your object will stay at rest. If the applied force is larger, your object's going to accelerate and move, so you're going to use a dynamics problem-solving strategy to determine acceleration. And in this case, when your object's accelerating and moving, you're going to use the kinetic friction equation since your object is moving. Atwood's machines and interconnected systems, okay? The keys, as a system is one whole, the acceleration is uniform for all objects in the system. So if we look right here, M1 and M2 are both moving and accelerating at acceleration A, okay? So internal forces, tension, contact between two boxes can be neglected in the overall system, okay? So if we're trying to find the acceleration for the overall system right here, we can neglect tension because tension is going to act up on box M1 and act upwards on box M2, so they're internal to the system. Their effects cancel out in the overall system. So what we do is we're now going to flatten out the system. We're going to take the direction of acceleration to be positive, and we're going to draw a free body diagram, okay? So we would flatten this out. M1 would be like right here, M2 would be right here, and then there'd be a line connecting M1 and M2. The pointer's not the best for visualizing that, but we've gone over these problems enough. Okay, and because our acceleration is occurring this way, because downwards on this side, because the mass M2 is greater, our acceleration is going to be positive, taking towards the right direction, okay, when we flatten it out. Our free body diagrams, when we flatten out, is going to have M1G acting to the left, again, when we flatten out, and tension acting to the right, and then M2 G will be acting towards the right, and tension will be acting towards the left on the M2 box. We solve for our acceleration in the overall system, and if the problem asks for further step of determining tension between the objects, we use the acceleration and the free body diagram of one object to solve for the tension. So once we've found the acceleration of the overall system, we can focus on one object and solve for the tension of that one object. Okay, so we can use Newton's second law. MA will equal negative M1 plus T, or negative M1G plus T, and we can use that to solve for T. Elevators and apparent weight. Weight is invariant in a local gravitational field. The apparent weight is a result of normal force, aka the weight will always remain the same regardless of whether you're bouncing up and down on a trampoline or you're standing on the ground. The apparent weight is a result of normal force, so the apparent weight is what changes when you're on a trampoline. So example 1, in midair you feel weightless, you still have weight, but there's no normal force acting on you midair to feel that sensation of weight. Example 2, if a car speeds up, you'll feel heavier as you are pressed against the chair, but your weight is actually the same. If the acceleration of the system is positive, then the normal force is greater than weight, so you will feel heavier. Okay, if your acceleration is negative, then the normal force is less than your weight, so you will feel lighter. All right, if you're moving at a constant velocity, which means 0, you're in equilibrium, so normal force is equal to weight, and you will feel the same. Again, this comes from the idea of a little bit of analysis, applying Newton's second law to this scenario. We have two forces acting, the weight, Fg, and the normal force. So we're going to have Fn minus Fg equals May. Solving for Fn gives us May plus G. So if Ay is negative, Fn will be less than our weight. If Ay is positive, Fn will be greater than our weight. And then if Ay is equal to 0, constant velocity, then Fn will be equal to mg, our weight. And lastly, we have inclines. Again, the idea behind an incline is that x is directed along the incline, while y is perpendicular to our incline. The gravitational force is broken up into parallel and perpendicular components. We have the equations here in a second. F parallel is mg sine theta. F perpendicular is mg cosine theta. The normal force is not equal to the force of gravity. Rather, it counteracts the perpendicular component of the force of gravity. On frictionless inclines where no other forces act, the acceleration is independent of the mass of the object. So if we have no friction acting right here, two objects of unequal masses placed on incline will accelerate at the same rate. Again, that goes back to the idea that in the absence of external forces, the acceleration due to gravity is the same for all objects regardless of their mass. Oh, guess we have one more slide. Air resistance, aka le resistant. Air resistance, aka air friction, attempts to counteract motion of an object in a fluid. So it could be air, it could be water. If you've experienced that in swimming before. So the microscopic factors in theory is that the surface area has a positive relationship with air resistance. The more surface area, the more area there is for collisions and contact. Speed, the higher the speed of an object, the more collisions there will be per second, and thus there will be more air resistance. And then the drag coefficient. It's a like coefficient of friction. It's a material property between air and object that quantifies the aerodynamicity of object. Ooh, that's a big word to say. All right. Essentially, it quantifies how well air or fluids flow by an object. So if your drag coefficient is higher, then that means you're going to be less aerodynamic, while if it's lower, it's going to be more aerodynamic. Mass has very little effect, to the point that we can neglect the effect that mass has on air resistance. Now again, here's an example right here. A person with a bigger parachute will be able to have more collisions happen per second, and thus more air resistance acting to slow them down. Thus why bigger parachutes tend to be more effective in keeping people safe. And that is our review for day 2.